saw that angular displacements are a little different than linear displacements or translational displacements in that they don't obey vector addition. The order of rotation matters if we apply a rotation to a piece. And we did this example where we saw where if we rotated first by x and then by z, we got a different answer than if we rotated by z and then by x. So this makes them a little more difficult to deal with. Fortunately, though, when we go to derivatives, we're talking about small or infinitesimal displacements. And if we have an infinitesimal displacement, then we can replace any sine theta functions with just theta, and that's the first term in a Taylor series expansion, and we can replace any cosine theta functions with just 1. That's the first term in a Taylor series expansion. There'd be a 0 times theta, and there'd be a theta squared term as well, but we neglect all of those. But in any event, we can neglect, or we can simplify these. If we replace all of these with thetas, these both just become 1. There's a 1, there's a theta x. And interestingly, for the other sequence that's in the other order, we end up with the same thing. And I think that's enough, you get the idea. But in either case, what we end up with is a minus theta z in the I direction plus a 1 in the j direction plus theta x in the k direction. So both of these are the same, and we conclude that these infinitesimal displacements do obey vector addition. So we can take advantage of that. And the way we take advantage of that is, again, in terms of calculating angular velocity and angular acceleration. By definition, angular velocity is the derivative of an angular displacement divided by time. And as we let delta t go to 0, this becomes small, and so the velocity components, or these displacement components, are infinitesimal. So that means that if we have multiple rotations applied to a part, say we have a rocket and it's rotating, about this axis, and maybe at the same time it's spinning about another axis, that we can just superimpose all of those rotations. Another thing I want to review that's important is that omega is a free vector. That is, if we calculate the rotation rate, about point A, B, or C for this body, they're all going to be the same. The angular velocity isn't a function of the point about which you define it. And so we'll do this for various problems. We'll define omega in terms of its various components. And we could do the same thing for the angular acceleration, which in this class we use the symbol alpha for that. And it's just the derivative of omega, and so a similar approach. Let's do an example to make this a little more concrete. So in this example, we have a platform that's spinning with a rate capital omega about the z-axis, and this rate is also increasing. We won't worry about that part for now. And then on the platform, we have a little motor and this wheel over here that causes this little part to spin around this axis with a rate phi dot. And we can add up those two rates and calculate the total angular velocity. The problem's asking what's the total angular velocity and total angular acceleration of this motor. with respect to an inertial reference frame. So we're going to do this example using more of a 202 approach. In the next lecture, we'll learn the preferred way, the way that we'll usually use. But first I wanted to show you this in a way that you might recognize from your dynamics class. By the way, these Greek symbols, omega and phi, if those names aren't familiar to you, you might as well go download a cheat sheet and learn your Greek alphabet. We don't have enough letters in the Roman alphabet for this class, so we're going to have to use some of these Greek letters. Okay, so anyway, how do we solve this? Well, using the 202 approach, we write both of these rotations and we add them up. So I guess let's just start here. In the simplest sense, omega is this rotation rate capital omega, and it's about some axis, and we'll say that axis is the E omega unit vector here. Now it happens that that's equivalent to the K unit vector, which is a fixed reference frame in this problem. But first we just write it in a general way. And then we're also going to have to add the rate phi dot, and using the right-hand rule, that's in the positive E phi direction, as pointed out there. And so these are the rates and their two unit vectors, and then we want to put them in the XYZ coordinates. So the first step of doing that is easy. We just replace that with K. But to do this second one, we need to use the approach we did last time. And that is, we need to draw a picture that has X and Y, and then draw this unit vector, E phi, and this would be our 45-degree angle. 45-degree angle. Or actually, I'm just going to call that, actually we don't have a name for it, I'll just call that theta to be general. So using the approach we did last time, we can break this into components, and so we can say that E phi in the most general case would be a cosine of theta in the I direction plus a sine of theta in the j direction. So putting all of that together, we get that omega is equal to the capital omega rotation rate in the k direction plus the phi dot rate in a direction that's cosine theta in the I plus sine theta in the k. So there's our angular velocity. And so this is the first half of the problem. And now if we also wanted to find alpha, which is just the derivative of omega with respect to time, we can do this in the usual 202 way. Because these unit vectors are fixed in space, we can treat ijk as constants. So we can just write this as omega dot in the k, plus we're going to have to remember the chain rule here. We'll have phi double dot times the rest of this unchanged. Notice that's just the E phi direction. And then we need another term that's phi dot times the derivative of the inside. So for the inside, this first term, derivative of a cosine, is a negative sine theta. And then we also have to take into account the derivative of theta with respect to time. And then we do the same thing for that second one. Derivative of sine is cosine. Oops. And then what's the, what is this d theta dt? Well, if we go back to the picture, theta increases as this wheel spins. So theta is the angle whose derivative is capital omega. So both of these are just the rotation rate, capital omega. And we have our solution then right there. So this is how you could do it using the 202 approach. This way works perfectly fine. For this problem, actually, it's no problem at all. We'll throw some problems at you later that are much more challenging, that'll make this more difficult. But this is one way to calculate angular velocity and angular acceleration. And in the next class, we'll look at the math a little more carefully and come up with a better way to do this. Until next time.